Okay, so here is where we are. We are going to be looking at atomic structure. We're going to start with the history, really, of chemistry. So our question of the day is, why do you think that scientists in the 20th century thought that it was important to unlock the structure of the atom? Go ahead and pause and answer this question in Canvas. Okay, moving on. So, when we start looking at the history of the atom, the first person that we really start to look at is Democritus. He was the first to theorize that all matter was composed of atoms. Now, atom comes from the Greek word atomos, which means dividable or not dividable or whole. His ideas, however, were crushed by another Greek philosopher. Yes, that's right, Aristotle has come into play. So he asked 3 questions. If we are made of atoms, what holds us together? Why can't we see the atoms? And why don't we fall down like a bag of marbles? Kind of interesting questions, and they made Democritus think that he was unable to really answer these questions. And so people continue to think that matter is continuous. Your body, the world around us, was one continuous piece. This philosophy continued for centuries. When we get to the Middle Ages, science was lost to this world. There was a controlling body that really held tight to what science was done and to what challenges were accepted. So really the only science that was done was performed by the Arabs out of Africa that had conquered Spain. They traveled from the Middle East to Western Europe. They carried with them the Library of Alexandria. So when the plague, the Dark Ages, millions were dying, the Moors had everything really. They had running water, they had dentistry, reading, writing, geometry, rudimentary calculus, complex gardens, and agriculture. Once that controlling body was overthrown, or there were people that challenged their authority, then we started to see a change, a shift. During the 17 and 1800s, scientists were discovering concepts and relationships. They were doing large-scale, observable, really basic experiments. Now, this was not to the lab standard we do today. This is more like kitchen chemistry. They weren't using microscopes or computers or anything like that. What they were using was basically stoves, pots, ovens, some basic glassware. A lot of glassware at this time was hand blown, so it had to be handmade. So the observable properties that they saw required explanation. That brings us to Joseph Priestley. He is the scientist that prepared pure oxygen, and he did that by decomposing mercuric oxide into mercury and oxygen. Also has some claim to early beginnings of soda pop, because he did discover carbon dioxide, and, of course, our favorite, laughing gas. So what he noticed was that when he heated the mercuric oxide, it burned a candle brightly. So this air that was released, he referred to as perfect air, or dephlogistated air. He thought that phlogiston, back at that time, this was a common belief, phlogiston was a substance in the materials, and that as the materials burned, this was released, and eventually that would cause the flames to go out. Now, do you really think that's true? No. So in reality, what he had discovered was oxygen. He just didn't realize it. So Antoine Lavoisier lived during the French Revolution. He was a brilliant scientist, but he was a tax collector. As such, he met his fate during that revolution. So what he proved was that substances did not give off phlogiston, but in fact used oxygen. He burned the metals in air, weighed them before and after, and what he found was that after they were burned, they weighed more. Well, that wouldn't make sense. If they were giving off phlogiston, they should weigh less. So his hypothesis is they weighed more because they were combining with oxygen. So he weighed materials before and after, and he came up with the law of conservation of mass, which states that matter can neither be created nor destroyed in a chemical reaction. It can only be converted from one form into another. So the extra mass must have come from the oxygen in the air, which was later able to be measured by reheating the compound that was formed. Fast forward, we get to Joseph Proust. Joseph Proust examined materials like copper carbonate and found that no matter how much you had or how little you had, if you decomposed it, you would always get 5.3 parts copper, 4 parts oxygen, and 1 part carbon. So it's a lot kind of like scaling up or down a chocolate chip cookie recipe depending on how many people are coming. So as a result, he came up with this idea of the law of definite composition, which states that all substances are composed of definite amounts of each element, no matter how much or how little of the matter there really is. So next in line, we start getting away from the times of Whigs to John Dalton. He was a school teacher, and he devised the law of multiple proportions. What he stated was that if there are two elements that form more than one compound, then they have to come together in whole number ratios. We're not going to split an egg, for example. So what does that mean exactly? Well, let's take carbon and oxygen, for example. Those two by themselves form two compounds, carbon dioxide and carbon monoxide. In carbon dioxide, what he found was that carbon and oxygen combined in a 3-part carbon to 8-part oxygen mass ratio. In carbon monoxide, it was a 3-part carbon to 4-part oxygen mass ratio. So it wasn't really obvious what was going on. They didn't really know what was making things come together to react. Keep in mind, they didn't even know atoms existed. So what they said is that, okay, if these compounds are coming together in ratios, there has to be smaller pieces. So, John Dalton theorized these substances were made of atoms. This led to the atomic theory of matter, which states that all elements are made of tiny, solid, indestructible particles known as atoms. All atoms of a given element are the same. If you have different elements, they're going to be different atoms. And they come together to form compounds in whole number ratios. 1 atom to 1 atom, 1 atom to 2 atoms, so on, so forth. And most importantly, the chemical reaction does not change the atoms, just how they're. With a small change, this is still used today. So that means that it's been 2,000 years, but the idea of the atom came back. So John Dalton brought back Democritus's idea. It seems simple, but still people did not think, they did not want to accept that matter was made of little marble-like structures called atoms. Now, John Dalton's theory did have a flaw. There was one area in which it was really wrong. Now, our atoms are not solid and indestructible like marbles. In fact, they contain different parts. We have protons and neutrons, electrons, at just the next level down. But scientists didn't really know this yet until those parts were discovered. So, what do you think was discovered first? Well, if you would have guessed electron, you would be right. So, why do you think it was the first part of the atom to be discovered? Well, partially because the electron is outside the atom. It's the only part of the atom we can take or we can add to with regards to an atom. It's tiny and light, and well, right now you're using electrons in the form of electricity, moving electrons. So, although technology wasn't that amazing hundreds of years ago, we were still able to find it. So we go forward a little bit and we get into the late 1700s, early 1800s with Benjamin Franklin. He did a lot of basic work with static electricity. He had rods he would charge with different fabrics, different animal furs. And so he had a lot to look at with electricity. His idea was that matter has charge. And there are two types of charge in the world. Positively charged objects, objects that he felt had a surplus of charge, and negatively charged objects, or objects that did not have a surplus of charge. They had a deficit. So Benjamin Franklin was the first to come up with these names. Now, he did not realize that the charges were part of the atoms. He didn't even realize the atoms existed yet. But what is important here is that even Benjamin Franklin made a mistake, because it's not positive that's the surplus. It's in fact negative. So just keep that in mind. Now, when we start looking at charges, there's something interesting to keep in mind. Positive charges will repel other positive charges. Negative charges will repel other negative charges. So like charges will repel each other and opposites will attract. So a positive and a negative will want to come closer together. So that takes us to Crookes tube. In 1879, Williams Crookes designed a tube. It was completely evacuated. We connected it to a vacuum pump. Think like fancy old-fashioned food saver. We had this glass tube. So inside this glass tube, we had two metal plates that were connected to a battery source, a power source. We flip on that power source, and in between those plates is a green glow. It looks kind of hinky. Crookes was convinced that this beam had to be charged particles. So, what exactly are cathode rays? Well, in 1897, J.J. Thomson took a Crookes tube and put charged plates above and below the beam. And what he found was that the beam was attracted to the positive plate. It was deflected from the negative plate. So from this he said, well, the beam has to be negatively charged particles. Let's call those electrons. So he was looking at them. They are part of the atom. So we can take those electrons, we can easily take them off atoms, and we can use them for electricity. So this is an up-close view of J.J. Thomson's experiment with the positive and the negative plates. So if we look at a cathode ray tube, glass tube, this is kind of what you see. There's that green glow. Now, another thing that he did was he said, okay, well, what if I put a magnet there? What he found is a magnet also caused the beam to deflect. So he was the first, really, to conclude that electricity and magnetism were related. And in fact, we call that science area electromagnetism. So, this ability to connect them was able allowed him to be able to calculate the ratio of the electron mass to the charge. This won him the 1906 Nobel Prize. Now, we talked a little bit about modern science. In some fields like physics, the line for modern science really is drawn about 1905, when the special theory of relativity came out. So keep that in mind. This is like dawning of a new age. So when we look at these beams, we can see that we are going to be getting them to bend. So what's causing the beam to move? It's always made of negatively charged electrons. Those are coming from the battery, a magnet, a charged plate. Those are what's going to provide that stimulus that will cause the beam to change its path. That will cause that curve. So when we look at old-fashioned TVs, the cathode ray tube was really the precursor to the modern day. So when we look at them, black and white, you can see that we have the electron gun. And we would change out about half of the screen frames, the scan lines, every second. We would be changing those out. So when we get to color, we have multiple electron guns. We would have phosphor dots. So there was a lot of science involved here in the original TVs. Now, if you remember these giant TVs, they had their own cabinets, or they were very large boxes, or the first computer monitors, those were built on the cathode ray tube technology. And that's where they got the name CRT monitors and CRT TVs, for the cathode ray tubes. Now, modern TVs, the LCDs, when we look at a single pixel, light is coming in, it goes through a polarizer. That means all of the light is then oriented in one direction. We go through a thin film transistor, a color filter, and then it is repolarized based on how much of that color needs to be on the screen in that pixel. So it's a fairly involved piece of technology. So we're going to pause here, and when we come back, we're going to look at Millikan's oil experiment.